continue our discussion on DC machines. Last class we discussed the principles of DC machines, and we discussed the EMF, how we can calculate the EMF of machine and the different windings techniques, lab and wave winding. Today, inshallah, we will continue discussing the DC machine principles. Okay. So we discussed last class the principle of DC motor. We used Fleming left-hand rule, and according to Fleming left-hand rule, we can identify the force direction, and based on the force direction, we can identify the motor rotation after that. So if you apply here Fleming left-hand rule, the flux direction will be in this direction from N to S, and there is a conductor here. If a current is coming out of the page, so the force will be on the up direction, and if it is the current if it is going inside the page or into the page, the force will be in the direction of a down direction, like that. Right. Also, we made a demonstration for DC motor operation, and we understood from the demonstration in last class the operation of the DC machine and the function of commutator. So let me ask you, Shabab, now, what is exactly the function of commutator in DC machine? Who can reply, Shabab?
Yes, doctor.
Yes, تفضل.
تغير البولاريتي.
So it's commutation here means makes rectification.
Yes.
For the AC which is inside the machine to DC which is outside the machine. طيب يعني in case of generator we can say that it's rectification because the EMF inside the coils will be AC. So we converted it to DC outside the machine. However, if it is in motoring mode, we convert the DC input voltage and current to make rotating AC EMF or rotating flux in order to rotate the machine. تمام يا شباب؟ يعني if there is no motor or generator, no electrical machine working without rotating flux. Rotating flux is nothing but AC flux. And the flux has to be AC in order to rotate the machine. So in DC machines, in order to make AC flux, we use commutator, which converts from AC to DC in generator or from DC to AC in motor. تمام يا شباب؟ طبعا I mean generator and motor, I mean generating mode and motoring mode, because we agreed together either motor or generator, both of them are nothing but modes of operation of the same machine. Right. From the discussed and observation of the videos last class, we can now start calculating the torque of the machine. Simply, Shabab, the force on each conductor equals, we know the Lorentz force law, so force equals B, flux density, multiplied by the L of the conductor, multiplied by the current flowing in the same conductor. So if we have now many conductors or many coils connected together in parallel path to make the overall armature winding, we can say that the conductor winding, which is the same as coil winding, equals to the current, the total armature current over the number of parallel path. So this is now represents the force on one conductor. Right. What is the relation between force and torque, ya shabab? Torque equal force multiplied by
SR.
Radius. What is the radius here? It's the radius of what? يا شباب, according to the structure of the
coil.
لا. Structure we discussed last class. Yeah, from here. This is R يا شباب. يعني R is considered at the midpoint of one turn to the end of the turn itself. يعني we can consider this length as R. And it's nothing but the radius of the rotor core itself. Or average radius. Okay? So this is now the considered radius. تمام يا شباب؟ طيب. Again. So we know now the torque equals force multiplied by the radius, which is the rotor radius. Right. This is now the torque for one conductor. What about the overall average torque يا شباب? How we can calculate? We can say now B multiplied by torque equal force multiplied by R. So force equal BLIA over barrel path A. So F multiplied by R will be P flux density multiplied by length of conductor multiplied by radius of rotor multiplied by armature current over number of a parallel path. If we substitute the relation, we can get a relation of L. Yani we have here B multiplied by L multiplied by R. If you get the value of flux in terms of B multiplied by A, okay, so you can get the relation as phi multiplied by number of poles multiplied by IA divided by 2 by A. Type. So this is now شباب considered as the torque for one coil or torque for conductor, which is considered as the average torque now. Type. For the two conductors, the resultant torque will be 2 multiplied by number of turns, which is Z multiplied by divided by 2, okay, multiplied by the torque for one coil or torque for one conductor.
Sorry, Doctor.
تفضل.
What torque it represent? The sorry? Torque of no, not the torque of the coil. The torque on the other side of the equation.
In this slide, you mean on previous slide?
Yes, in this slide. T equal.
This torque is the overall torque now.
Overall torque.
Yes.
Okay.
Compared to the torque of conductor, so you should multiply by number of conductors. What is the number of conductors? It's 2 multiplied by number of turns. صح? Or we can say Z multiplied by TC. تمام يا شباب? We said in the last class we have Z equals N over 2. Z. We define Z as number of conductors, and N is the number of turns. And we agree together that one turn equals 2 conductors. This is conductor number 1, this is conductor number 2, and all considered as one turn. So number of turns equal to number of conductors over 2. تمام يا شباب? So we can say now the total torque or the average torque for the overall machine equals to N multiplied by, you can now substitute by the torque of one coil, so multiplied by flux, number of poles over by A multiplied by current. And we know before that N multiplied by number of poles divided by A is nothing but the machine constant, Ka. So we can say now torque equals Ka multiplied by phi multiplied by armature current. So now, Shabab, we have two relations which are important in DC machine in terms of the magnetic flux or converting from magnetic flux to electrical circuit. We have, or electromechanical device, we have torque, which is equal to machine constant multiplied by flux multiplied by current. And we have the other relation which we have already proved in the last class, which is EA, the back EMF, equals the same machine constant multiplied by flux multiplied by speed of the machine. So these are considered the two relations needed for electromechanical device, for DC machine electromechanical system. تمام يا شباب؟ So these are the two equations يعني we need or we observe it from the definition and from the principles of the DC machine. Later, inshallah, we are going to use the two relations directly with electrical circuit. We don't need to start from scratch every time to solve a problem. Just we are going to use the final two relations in the different types of connections. We have many connections in DC machines, and we are going to describe all inshallah in details and what are the differences. Tamam? So we have now two relations, which are E equals Ka multiplied by phi multiplied by omega m, and the other relation, which is torque, equals Ka multiplied by phi multiplied by Ia. These are the two important relations now. Type. In terms of power يا شباب, now when you supply a motor, there will be some losses, okay, some electrical losses on the coils itself, on the coil equivalent resistance, which we call it copper loss, okay, like what we described previously in transformer. And after that, you will find also you have some core losses, okay, and the resultant power or remaining power will be converted from electrical power to mechanical power. This is called يا شباب developed power or electromechanical power. تمام? Again, this power is called developed or electromechanical power. This power here is considered as EA multiplied by IA. Okay, so this is considered as the electromechanical power, which will be converted from electrical to mechanical power. So what will be the equivalent mechanical value? It should be the same value of this one. So if you now substitute in EA, IA, substitute EA by the relation Ka phi omega m. So you can find that Ka phi omega m multiplied by Ia. And you know that Ia multiplied by phi multiplied by K is nothing but torque. So we can say now EA equals torque multiplied by omega m. This torque is called electromechanical torque or developed torque. And omega m is the rotor speed. So we now could convert from electrical to mechanical. So EAIA, developed power, is equivalent to torque multiplied by omega m. This is just to understand the electromechanical power of the DC machine. Later on, inshallah, we will discuss the power flow in more details for all of the machines type. Is there any question, Shabab, regarding this part? Is it clear?
Doctor, omega m, what does it represent? It's not clear.
It's rotor speed. Okay. This is the machine speed. Let's have an example regarding the machine windings in order to understand more the construction and the shape internally and how the machine is working based on the different connections. This example says we have 4-pole DC machine, has an armature of radius 12.5 centimeters and an effective length of the rotor itself, okay, of 25 centimeters. So we have DC machine has armature. Armature means the armature winding, which is inserted on the rotor of the DC machine. Has a radius of 12.5 centimeters and length of 25 centimeters. The pole covers 75% of the armature periphery. It's very important, which means you have now 25% of the windings not facing the poles. So the effective area now will be only 75% of the overall area. تمام يا شباب؟ طيب. The coil or the armature winding consists of. تفضل.
Could you repeat the 75% point because it was lagging? I couldn't hear you clearly.
No problem. Now the problem here say the poles cover 75% of the armature periphery. يعني ايه؟ يعني if we have a look here يا شباب, we have quarter section of the machine. So this is now considered as one of the poles because we have 4 poles and these poles will cover the 100% of the machine. However, it's stated that the pole cover 75%, which means this is 1/4 of the machine. So the pole only exists in 75 of this quarter. So it's not covering all of the periphery of the machine itself. So you can consider now the area as 75% of the pool or of quarter of the machine. This means that the flux, which is going to move.
We can't say only 3 balls is enough, like because it's 75.
لا طبعا.
Couldn't we just?
يعني in calculations you are right, يعني because it's 75. However, in reality it's 4 balls. تمام? So we
I meant in calculations
as 4 balls and area is 75%. Okay? يعني if we consider يا شباب machine, يعني machine cannot work with odd number of balls. يعني how it works, يعني all of time the flux is moving from N to S. So in order to have flux pass, you have to have 2 poles, N and S. So يعني if you have a third pole, how the flux is going to move? However, if you have 4 poles, this is mean you have NS, NS, so the flux can move in 2 directions, from one SN to another S, and from the other N to the other S. This is the way. However, we cannot have odd number for any machine. All of poles have to be even number. Type. The armature winding consists of 33 coils. So this is the number of coils. Each coil having 7 turns. For this شباب, how many conductors now we have? We have 7 turns, 33 coils. So how many conductors?
2, 7, 33.
So we can say now that number of conductors equal 2 multiplied by number of turns, which is 7, multiplied by 33. So this is now number of conductors per winding, because we have 33 coils in the windings, we have 7 turns in one coil, and 2 conductors per turn. So this is now considered as the overall number of conductors of the machine. Okay, Shabab, is it clear? The coils are accommodated in 33 slots. And this is not important now for us. The average flux density under each pole is 0.75. So this is the given flux density. So this is B. Right. What's required here? If the armature is lab winding, find the armature constant, Ka, determine the induced armature voltage when the armature rotates at 1000 RPM, then determine the current in the coil and the electromagnetic torque, which is the developed torque, developed when the armature current is 400 ampere. Then finally, determine the power developed by the armature. This is if the armature is lab winding. Then we will repeat all of these parts where if the armature is made or connected as wave winding technique. Type. Let's start from the lab winding. We know, Shabab, from lab winding, you know, the relation of Ka equals NP divided by A. This is the relation of KA we already proved in the EMF derivation in the last class. So N equals Z over 2. So Z over 2 multiplied by number of poles over A by. We calculated the number of conductors as Z equal 2 multiplied by 33 by 7. So this is now the number of conductors. And here in lab winding, we have the number of parallel paths equal to the number of poles. The machine here is 4 poles, so A equals 4. Now you can substitute in the relation and get the value of KA. So this is now the value of KA. Right. After that, it's required to calculate the induced armature voltage when the armature rotates at speed of 1000 RPM. So, in order to calculate the EMF, you know the relation of EMF, E equals KA, we calculated KA, multiplied by phi, multiplied by omega. Phi equals B multiplied by A. We have B, however, we need to calculate A first. So, what is the A or effective area of the winding now? If we consider that we have one ball like that, ya shabab, we have radius of the circle of the inner circle of the rotor, which is R, and the length of the conductor is L. So we can say now the area under this ball equals to 1/4 of the area of internal or internal area of the cylinder. صح يا شباب؟ and we have 1/4 of cylinder, and the internal area of this cylinder equals to the circle periphery, which is 2 by R multiplied by the length. تمام يا شباب؟ So we can say now 2 by R L, this is considered as all of the cylinder area, divided by 4, because this is for one ball, and also multiplied by 75%, because we said the pole is covered only 75% of the overall periphery of the rotor. So we can say now 2 by RL, we have R and L of the terms or conductors, multiplied by 0.75 divided 4, because we have 4 poles. تمام يا شباب? So this is now considered as the effective area for one pool. So we got the area. Now you can simply multiply the area by the magnetic flux density to obtain the overall flux. So phi equals to A multiplied by B. B was given as 0.75 Tesla. So simply we could calculate the value of flux. So the flux is 0.0276 Weber. This is now the value of flux. Simply we can now substitute in the equation of EMF. So EMF equals KA, we already calculated. Flux we obtained, and omega is given. Omega equals 2 pi over 60 multiplied by the speed in RPM measured. Okay, so this is now the value of EMF for this kind of winding. Right. Is there any question, Shabab, regarding this part? Is it clear how we could calculate the area and give the EMF?
Doctor,
تفضل.
the graph above, what does it refer to?
This is 1/4 of the machine now. And if we assume that we have the overall machine, okay, this is considered as 1/4 of the machine. Okay, this is internal section from the cylinder, but just a quarter of the cylinder, okay, which represent one of the balls of the 4 balls here. The length is L, and the radius of the circle itself equals R. Okay, so this represents now the parts or quarter part of the machine. Now, is it clear?
Yes, yes.
Yeah, okay. Regarding the coil current, Shabab, we have the overall current equals 400. So if we now would specify the current of one coil, we should divide by the number of parallel paths. And we have here lab winding where A equals number of volts, so we can simply say the coil current equals total armature current over number of parallel paths. So it's 100 ampere now. Fine. For the torque, you know that torque relation, torque equals Ka multiplied by phi multiplied by the armature current. This is overall torque and this is armature current. So we have Ka and phi. We calculated phi already and Ka, so we can simply substitute in the relation and get the equivalent or the overall torque. As you can see, the torque here is huge for this machine. It's 811.8 Newton meter. Regarding the power, شباب, the electromechanical power or developed power, we can calculate it in two different ways. We can say it's EAIA or torque developed by omega m. We have EA, which is 212.5, we calculated in the previous slide, multiplied by the armature current. So this is now representing the machine power, the machine developed power. Or we can calculate it using torque multiplied by speed in radians. So it's 1000 RPM multiplied by 2 pi over 60. So it's equals to 58 kilowatt, the same as the other way of calculation. Right, this is regarding the lab winding. Regarding the wave winding, for wave winding, we have number of parallel paths equals 2. This is used to increase the voltage of the machine. So in this case, we can substitute again in the relation of Ka. It will be different because Ka depends on the number of parallel paths. So if you substitute now, you will find the relation, the value of Ka equals 147. Previous one, if you remember here, it was 73. So this one is 2 times the previous one. Okay, so this is now the new value of Ka according to the wave winding. Now we need to calculate the EMF again. So use the same speed and the new value of Ka. You can say EA equals the relation EA equals Ka multiplied by phi multiplied by omega m. So this is Ka, this is phi, and this is omega. So you can see now the voltage here of this A connection. As you can see, volt here is 425. If we compare this to the EMF for the previous case, it was 212. So now the voltage is twice. تمام يا شباب؟ طيب. Regarding the current, now for this connection, as you know, the coil is the same as the previous coil. We are not going to bring new windings. The same windings of wave and lab will be the same. So this means the current of the coil should be the same. The current of the winding itself should be the same because it depends on the cross-section area of the wires. So شباب, we have to respect the coil current, which is 100 amp. So for this kind of machine, if we make it as wave winding, the overall armature current will be lower. It will be 100 multiplied by 2 only, not by 4, because we have here 2 parallel paths. For that, here the current of the armature will be 200 ampere. If we now would like to calculate torque and power, simply you can calculate by the same way. Torque equals Ka multiplied by phi multiplied by armature current. So you will find the torque here is the same like previous, because Ka is twice and the armature current is halved. So we can get the same value of torque and the same speed. So the power will be the same. As you can see, power equal torque multiplied by omega or E multiplied by IA. So we can get the same value of power. So we could understand here, if we change the connection from lab to wave, this is going only to change the armature current and EMF value or voltage of the machine. However, the power will be the same. The torque also will be the same. Okay, شباب? So it's just a way to increase or decrease the rating current or voltage. تمام يا شباب؟ Is it clear? So this is now for the same machine construction. طيب. طب now we could understand the operation of the machine, and now we would like to convert this to magnetic circuit and then to electric circuit in order to make analysis for DC machines. So let's now imagine together we have rotor inside, and this is the core of the stator. We have two poles in the machine, for instance. So we expect that the pole, assume this pole is N, this one here is N, and this one is S, according to طبعا the winding of the field, the direction of field windings. تمام? This is going to make this, for instance, N, and this is S. So we expect that the flux is going to move in this direction. And after reaching to S, it will return back again in the yoke of the stator itself. Again here, for the other path, it will move in this direction and return back in the yoke. تمام? So we can now obtain the magnetic circuit from this configuration يا شباب. So we have two sources for MMF because we have two coils. So here, as you can see, we have one FB, which is MMF, and this is the other FB. So this represents at pole S and pole N. So as you can see, this is F1 and this is F2, or F at pole N and this is F at pole S. And the flux is going to move across many things or many materials. As you can see here, flux path through the pole. So we have reluctance for the pole itself. Air gap, so we have another reluctance for the air gap. Rotor teeth, rotor core, rotor teeth again, okay, because it's going to move through rotor teeth from here and through the core and return from the rotor teeth again and go to the air gap and pole and so on. So this is now the travel of the flux. This is a travel path of the flux. So we can consider now we have R of pole, R of the air gap, R of teeth, R of the rotor itself, then teeth again, and air gap, and then the MMF of the coil, and the pole again. So these are the flux path, okay, in the middle part from pole to pole. Then as you can see, the flux will be halved. One half will move in the yoke, in the upper yoke, and the other flux, or the half of the flux, will move in the lower yoke. So we have reluctance for upper and lower yoke like that. طيب, as you can see يا شباب, يعني the circuit is complex. تمام؟ يعني if you need to make accurate model, you should include all of these reluctances in your calculations. However, if we assumed the operation of the flux in linear parts, and we can assume that the reluctance of the core itself is very small compared to the reluctance of the air gap, in this case, we can simplify the circuit like that. The circuit will be just the reluctance of the two air gaps and the overall MMF of the two poles, and we can consider that the reluctance of the yoke is also zero, if we assume infinite permeability for the magnetic core. So from this circuit, شباب, we can say that flux equals flux, which will represent the current. So we have here flux like that. Like current, if we need to calculate the current, we will say summation of the voltage over summation of the resistance. So similarly here, we will summate the MMF, so 2 multiplied by FB over 2 multiplied by reluctance of the air gap, which is FB over RG. So this now represents the flux in our machine. Right. So after considering this flux, we need now to understand the magnetization curve. What is the relation between the flux current and the resultant EMF on the machine? as you can see يا شباب, if we flow a current in the winding of the field, so this is going to make MMF, which is nothing but MMF or F equals M of field winding multiplied by I of field winding. And the resultant flux which will be obtained will be in linear mode like that after reaching saturation, okay, curve and saturation because of the core itself. This is the actual case. However, if it is only gap, it will be linear. There will not be any saturation. Okay, so this is now considered as actual case. Right. We can now say that this MMF, if we consider N as constant, this MMF can be represented as current. So here we can say that this is considered as field current. Okay, and flux, you know the relation between EMF and the flux. EMF equals K constant of the machine multiplied by flux, which will be the same response, multiplied by omega, which is the machine speed. If we consider certain machine speed now, we can say if omega m is constant, so the relation of EMF will be the same like the relation of flux. So this now, shabab, will be the relation between EA, induced voltage of the machine, and IF, field winding of the machine. So this is now the magnetization curve of DC machine. If we have different speed, ya shabab, yani, so if we assume this is at omega m, if we have different speed, yani for instance 70% of omega m, we have to substitute and make another curve at 70% of the speed. Okay, shabab? So this is the relation between I, EMF, and the field current, okay, which is corresponding to MMF and generated flux. As we just described, if we obtain this curve at certain speed omega, if we have omega m over 2 speed of the machine, so it's expected that the MMF, the EMF will be reduced like that, shabab. Okay, so this is now how we can represent EA or back EMF with the field current. So this is now the elementary shape of our DC machine. We need to convert this to an equivalent circuit, shabab. So you have internal windings for the rotor, and these windings are connected through the commutator and the brushes connected to supply. So this is now the way of the connection of the motor itself, and we can assume that there is a flux coming here from N to S by means of another circuit. We call it field circuit. So as you can see, we have here field circuit can be supplied through a DC supply here. We can call it as VF, and there will be a current moving here equals IF. This current will produce flux. That flux will cut the rotor windings and produce a EMF on the rotor winding itself. This EMF, which is EA, okay, and you will have some voltage drop on the brushes here. So we can say that we have some electrical voltage drop here equals to V brushes, and also you will have some electrical losses over resistance as well, okay, resistance of windings. So we can say that we have another resistance here representing the circuit and armature winding. So finally, we can say that we have field winding. However, field winding, shabab, most of times needs variable resistance in order to control the field current. So we should add R adjustable or field winding resistance, adjustable resistance with the field. So we can consider now RF as variable, okay, and it will be supplied from fixed source VF. And for the armature winding, we can assume that we have now total armature resistance, which will include the armature winding and the resistance or equivalent resistance of brushes, okay, or sometimes can be excluded, and this is now the EMF of the machine. So this is now the equivalent circuit شباب of DC motor. Armature winding and field winding circuits. Right, regarding the circuits, we can have many connections for these two circuits شباب. يعني as you can see, we need now supply for field and another supply for armature. Is it right شباب? So we need two sources, one source for field and one source for armature. So we have many techniques used to connect between the two windings. These connections are, يعني, as you can see here, we have many types of connections. We have shunt winding. Shunt winding means you have the start from shunt winding here. Shunt winding, it means you have field winding, it is connected in parallel with the armature. So we can connect both of them together to the same source here. This is called shunt winding. Series winding like that, شباب, okay, which means you connect the field winding in series with the armature winding itself. However, here we need some a special design because this field winding has to operate with the high current of the armature. يعني we will discuss this in details inshallah. Here it's stated shunt winding يا شباب, يعني shunt here is not accurate word in the textbook, but يعني this should be here stated as separately excited. This is separately excited. But he all of time in the textbook refer by the meaning of shunt winding to the field winding. يعني he means here the field winding is connected, is disconnected from the circuit, so it has separate source here. Okay, assume for instance this is positive and this is negative, so it needs external source. So this connection is called separately excited. Type. Now we have shunt, we have series, we have separately excited. We may add extra windings to the machine. These extra windings are going to connect the machine here. As you can see, this is the field and this is the armature. We connect extra series winding here. This is called long shunt. Why long shunt? Because the shunt winding or the field winding is connected across two long arms now, which is series winding and armature winding. So we call this as long shunt connection. We have another connection of the series winding like that between supply and armature. In this case, we call the shunt winding or field winding as short shunt. So these are the different connections, شباب. We have series, we have separately excited, we have parallel or shunt, okay? We have series winding in long shunt and series winding in short shunt. And we are going to discuss, inshallah, all of these connections for the DC motors. So this is simply the different connections. Okay, we have shunt windings. The shunt winding has large number of turns and takes only small current, around 5% of rotated electric current of the armature. So if we design to add the armature and field winding in series, we have to respect this current. So the series winding here has to be designed in different way to work with the armature. Okay, so series winding, the series winding has fewer turns but carries large current because it's in series with the armature. Yeah, this is now like a chart for the different connection. We have separately excited where the field and the armature windings are separated. We have self-excited like series, like shunt, like compound. Compound means either long shunt or short shunt. I believe the time is not sufficient to continue this part. We will start the separately excited motor from the next class, inshallah. Any questions, شباب?